So a moment ago we were talking about supersaturation. We said this reaction here can actually go both ways. This reaction can go both ways.
So we can change it back?
Yes. Now listen. Listen. Tyler, you need to put the book away. Okay. Whenever the reaction is going in this direction, it's giving away heat. If I put the heat back in this and put into this reaction, I can make it go back over here and separate these ions again and get it ready to use again. Okay? So this reaction can go both ways. All right? Because it's a supersaturated solution. All right? This ability to go both ways means that there's an equilibrium here. It's called an equilibrium. Okay? Equilibrium is a balance, is a kind of balance. But most of the time in chemistry, Taylor, we are talking about, when we say equilibrium, James, Schuyler, when we talk about equilibriums, what we're talking about are something that's more than just a balance. It's called a dynamic equilibrium. A dynamic equilibrium. A dynamic equilibrium means there's constant change going on, but there's nevertheless a balance. There's constant change going on, but there's still a balance. Okay? Think about it like this. Whenever the bell rings, students are moving around. They're moving from A wing to B wing and from B wing to A wing, aren't they? But at any given instant in time, the number of students on A wing and B wing is about the same. Because however many students are going from A wing to B wing, there's an equal number, roughly an equal number of students from B wing going to A wing. So every time the bell rings, there's a dynamic equilibrium going on. Constant change, but a balance nevertheless. Does that make sense? Yeah. Now there might be more students on B wing overall because the classrooms they have a few more classrooms over there. Okay? But there's still the number of students in B wing and the number of students in A wing, that percentage stays about the same all the time. Regardless of the fact there's more here than here, the balance stays the same. Does that make sense? Okay? A dynamic equilibrium is like class change all the time. All right? So, now this is a salt, sodium and carbonate. That's an ion right there. Let's use a slightly simpler salt here. Sodium chloride. And let's dissolve it in water. We did this before. We used that as our example previously. Okay? But in this case, I want to have so much sodium chloride in the beaker or solution, whatever container it's in, that I can't dissolve all of it. Okay? I cannot dissolve all of it. And that's what we're doing in those containers over there next to the wall. We're stirring up so much material in there, so much salt. We've got some magnesium sulfate in one, and some calcium chloride in another, and some sodium chloride in a third. And we're getting so much in there that it cannot all be dissolved. I think the one on the far left with the magnesium sulfate is already at that point where there's some magnesium sulfate we cannot dissolve. Or is magnesium sulfate? No. The one in the middle is sodium chloride. Well, see the clumps at the bottom of the magnesium sulfate in the corners? Anyway, there's so much salt in there that some of it remains on the bottom in clumps. Okay? So most of the time, when we think about this, we think that there's some sodium and chloride ions in this solution, and there's some solid sodium chloride down here. In fact, there's a dynamic equilibrium. Even though you can't see it because ions are too small to see, there are ions of sodium and chlorine that are dissolving. While at the same time, there are sodium and chloride ions that are in the solution that are joining up with the solid. So the dynamic equilibrium exists, even though you might not be able to see it. And we know this as much as we know. We don't know anything in science. Remember, in science, we don't prove things. We offer proofs of things. Okay? We have evidence that things exist. We never prove it in science because science wants to be testable. Needs to be testable. And so the experimental evidence is pretty strong that this process is going on. All right? So constantly, sodium chloride crystals are breaking up and forming ions in the water. They're being solvated. While at the same time, there are sodium and chloride ions that are rejoining and making a solid all the time. All right? And that creates what's called a dynamic equilibrium. Constant change, but an overall balance, like the students in A and B wings at Dorman. Does that make sense? Okay? That's one kind of equilibrium. But there are lots of different kinds of equilibriums. This reaction also obeys an equilibrium. Okay? This reaction also obeys an equilibrium. Now, this reaction, you just take air and put it in a vessel and get the conditions right with pressure and temperature and water droplets and things like that to make ammonia. Okay? But it is a constant battle getting the ammonia to form. It's the precursor. It's a reaction you have to do first before you make man-made fertilizers. Okay? Because most plants we grow for food cannot what's called fix nitrogen. They can't take nitrogen out of the air and use it for their building processes. There are a few plants that can. Soybeans, for example, can fix their own nitrogen, but corn and wheat cannot. So we have to put, well, what we do is we put nitrogen fertilizer in there. A lot of you put nitrogen fertilizer in your lawn. Okay? It's also the precursor to make most explosives. Huh? I can't hear you.
Manure.
Okay, manure has fixed nitrogen in it. Manure, what happens is those plants that can fix nitrogen decay into the soil. Plants that can't fix nitrogen then uptake that. Animals eat that fixed nitrogen, and when they defecate manure, then that fixed nitrogen is available for new plants to use that. So it's a cycle. It's called the nitrogen cycle. Okay? All right. So what, all of these dynamic equilibriums, this is a dynamic equilibrium, this is a dynamic equilibrium, this is a dynamic equilibrium. Okay? Because there's constant change, but there's an overall balance. Okay? Now, the overall balance exists until you change the conditions. The overall balance exists until you change the conditions. I said we have to keep this under pressure to make it work. Okay? So then there's all dynamic equilibriums obey something called the Le Chatelier principle. There's a capital C there. The Le Chatelier principle. And what the Le Chatelier principle says is that when a pressure is applied to an equilibrium, when a pressure is applied to an equilibrium, now remember the equilibrium is the balance between the two sides, okay, or the two reactions. When a pressure is applied to an equilibrium, the equilibrium changes to a new equilibrium. When a pressure is applied to an equilibrium, the equilibrium changes to a new equilibrium. All right. So if this reaction requires pressure to go in this direction, what happens when I lower the pressure? It goes back this way. If adding pressure favors the forward reaction, if added pressure on this reaction, air pressure, remember force to an area, is applied to this, then the reaction, it favors the forward reaction. When you reduce the pressure, it favors the reverse reaction. Okay? What can we do to the dissolving of table salt that would increase the amount that's dissolved? What? Add more? So if we add more over here, we're going to get more of this dissolved?
Wait, what was the question?
What can we do to dissolve more table salt? So normally if we put so much table salt in water, we get salt at the bottom. Is there any way to get the rest of that salt to dissolve?
Can you read the definition one more time?
Well, sure, we could add more water. That's true. But what if we don't add any more water? Is there anything else we can do?
Stir it.
Stir it.
Add heat.
Or is it like
But once it reaches equilibrium, when you stir it, it's just going to fall back to the bottom.
Add heat.
Heat. Heat would unbalance that.
Can you read
Okay?
the definition one more time?
Le Chatelet principle states that anytime you add a pressure to an equilibrium, the equilibrium changes to a new equilibrium. The balance changes to a new equilibrium. Now, in this case, the heat we added to this unbalanced the equilibrium. It made it such that these two, we could create more of these two things than this. Now, it doesn't do it a lot, but salt does dissolve more when you heat it up. Sugar does it a lot. So if I'm dissolving sugar, heat adds a great pressure to the equilibrium. Does that make sense? Now, when we're talking about pressure in terms of equilibrium, you need to know this. When we're talking about pressure to an equilibrium, we're not talking about force to an area. When we're talking about pressure to an equilibrium, we're not talking about force applied to an area. It's not that kind of pressure. We talk about anything that changes the way the equilibrium is working. Anything that can cause the equilibrium to shift. Okay? Anything. Now, technically, adding more water unbalances the equilibrium. But that only works as long as there's still some sodium chloride that can't be dissolved. So adding more water allows you to dissolve more. Once you get enough water in there, you can dissolve all of it. There's no equilibrium anymore. Does that make sense? So I can add water to dissolve more, but only as long as solid remains. Okay? Does that make sense? Okay. What are you supposed to do tonight for homework?
15 and 27.
Okay. Makeup test if you're doing it. Okay?
Makeup test